All right, so let's get started. So I have quite some new material to cover today, and so that will be a kind of a logical end of this long chain of theory that we have since the start of the course. I will not repeat it as we did yesterday. So we are now in the module covering formal knowledge representation for interoperability reasons. I mean, if we just take the down-to-earth application. And in this module, so we started with a framework for understanding a necessity of a language for describing objects in the world, and then gradually added more complexity and arrived to ontologies, which basically which is a formal representation of knowledge in a particular domain. So it has a vocabulary, and this vocabulary describes concepts, relations, constraints, and they're used for, again, for interoperability, for reasoning on this um, formally represented knowledge. So underneath the ontologies, so we have these three concepts: RDF, RDFS, OL. OL is the most expressive of the languages. So RDFS is already good enough for creating simple ontologies. OL offers much more than RDFS. So all has behind itself a logic concept, and this logic is called description logic. So this logic enables reasoning about the stuff that you describe in the ontologies, relations and such. And today, I have two goals. I mean, first, we want to see what kind of reasoning it is possible, because it is somewhat restricted. And restricted for a purpose, because for starters, we want to do these checks or inferences in final time. And also because, I mean, not all variety of reasonings that you can find in the course book is actually needed in practical cases. So you can, in practical applications, you can get away with substantially smaller subset of rules and types of inferences. What we will do, we will cover something which is called ALC. So ALC is a acronym for Attributive Language and Complement. And this is the most minimalistic logic behind ontologies. So I have a slide later on showing like 8 more of increasing complexity and expressiveness, but they are all can be viewed as extension of this one. So this ALC logic is the simplest one to demonstrate how and what kind of inferences are possible, and also how reasoners are implemented. So basically, ALC logic, well, it is defined by this 5 bullet points. So it defines concepts and properties, concepts and their properties, as well as individuals, so the instances of classes. These 3 logical operators and only these two quantifiers. So nothing more than that. So and as you can see, I mean, you can do very limited, I mean, types of inferences with this stuff. So let's talk about syntax. Again, so you recognize the symbols from the first part of the course. They all bear same meaning. So maybe some clarification is needed for the existential and universal quantifiers. So when you see a record like this in other slides, so it means that R is an individual, and so all related, all individuals belong to concept C, so that comes after dot. And here it's at least one, so that's the meaning of this. I will jump through several slides because I mean you can read these definitions offline. What is more important is to give some maybe examples of what can you do with this reasoning. But I mean with ALC. The reasoning boils down to these three checks. So sometimes you, I mean, maybe at first glance you wouldn't regard it as reasoning or inferences. So it's really checking the checking certain facts about or certain properties about the knowledge records that you insert in the in your ontology. So those are subsumption checking, so consistency, and instance checking. So if a specific individual belongs to a given concept. So let's talk about this example. So we have, so in all examples that I will show you now, it all boils down to very simple facts. So, so we have a definition of a parent stated like this. So in normal language, it reads that a parent is someone who has at least one child. So this sign is someone or something. So in ALC, you can define. So you have this negation operator with help of which you can define, for example, the property of being childless. So basically, now the reasoning would be if you present an assertion of this kind. So this is assertion. You remember. So you have A and T boxes in ontologies. So T boxes are concepts. So T boxes here are this first bullet, two bullet points, and in the third bullet point. So this is an assertion about particular individual. And the reasoning here would be, so if you have this assertion, you want to infer that this individual doesn't have children. So again, briefly to show you all other possible logics that exist in all, so you can choose in which in all you can define or you can identify profiles. So the expressiveness of logic you are working with. What does it mean? It means that if you need a more complicated language to describe your relations and between concepts and individuals, you can do that. But then it should be supported. It should be supported first by the language itself, and secondly, it should be supported by the reasoner. So that works with this kind of definition. So what you can see here is that based on this very simplistic logic, you can on top of it you can add, for example, role hierarchies. Then or you can add inverse roles. So it's so basically you can see all these acronyms as this logic with extra features that you can use to describe your domain. And then as you have these extra features, then you obviously can perform more complex reasoner, and then your algorithm should support it, basically. But we stick to ALC. So if you want to know more, I guess you can read it yourself when you really have a need for. But we stick to ALC because on this example, I want to demonstrate the classical reasoner. So how the principles of reasoning algorithms. So whatever you describe in your ontology, it has corresponding logic representation. So pretty much in the same way as we talked about a couple of weeks ago. And then internally, so that's important to bear in mind. So all these facts internally they are represented as triples, and the triples describing certain ontology, so also referred as knowledge graph. So that's you can sometimes see this terms as synonyms, and knowledge graphs and ontologies. Right, and so we need to be able to scan these triples and find the answers to this inference tasks that we have. And today I want to contrast two approaches. One which is a classical approach, so that was developed long time ago. So I mean, starting from I don't know. Beginning of 80s, and the most popular reasoners that exist nowadays. So they were created around end of 1990s, 2000s. I linked, or at least in the PDF, you will find a link to the survey of all mainstream reasoning algorithms. But the common to all of them is a concept of tableau. When you see this word tableau, tableau is a model. Of your knowledge graph. So, but now kind of this is a computer model that can be taken for processing and satisfiability checking. So pretty much in the same sense as we discussed previously. So what's needed to be done? So you again, so you scan your ontology, and so you have this four, in the case of ALC, four main inferences like consistency checking, etc. So you, for example, you meet an assertion. So you always start with assertions of individuals. and then for this given assertion of a fact, so you need to verify that this assertion is supported by the knowledge base. So again, in exactly the same manner as we talked about model checking for the predicate logic. So any sentence should be supported by the rules you have in the knowledge base. And if it is not supported, then it should be it should raise a flag. So there is an issue. So what you see, the manifestation of it, you will see as a kind of not warning, but an error message that your ontology is inconsistent. So this kind of inferences is a kind of, I mean, to me, I have this analogy to compiler. So it's like compilation time checking. So whatever you write, so you inference, I mean, whether it makes sense with respect to the knowledge base. So here it is. And then, so when you meet this assertion, so you start to build a model out of it. So based on the rules you have, and the facts presented in the assertion, and this is called tableau expansion. So you start with a single cell, and then you kind of branch it based on the information available in the knowledge base. So, for example, we have, oh, that's a different level, sorry. So we have one T box, so the concept level statement, so which defines a person as a subclass of uh, uh, that's a little bit mind-bending. All persons have persons as yes. Person is a subclass of a people who has persons who has child. Does it make sense? So if our parents are persons, they have children, and children are persons. So that this kind of very sophisticated logical chain. And then we have an assertion that an individual John is a person. So now, so we type this rule into a knowledge base, so in Protege, like we discussed yesterday. And then we created an instance, so sometime along the way, that John is a person. So what happens behind the hood now? So now we need to check whether this assertion makes sense based on the availability of conceptual description. So we need to check satisfiability. And in this case, I mean, this type of inference, the consistency inference. So we need to list, starting from this assertion, so we need to expand it to all possible models again. So now you should have an allusion to vault models that we talked about in the first part of the course. And we need to find whether there is a model that in which this statement holds. First, you need to convert it to some normal form, DNF, CNF, or negation normal form, and you start building your model. You build a model with an individual. So as I said, so you find an individual and you start building a model. What does it mean? So let me see. So graphically, so you build a tree of nodes. So where the root of the tree is your assertion, and each node has each node has a name, so the individual, and a label. So the one that here we will collect everything related to concepts being present in our ontology. And now we are ready to expand it. For expansion, so I will not spend time going into the definitions. So we have a number of rules, well, 5 of them, on how to treat different operations, different logical operators, and quantifiers during the expansion. Some of the rules I will demonstrate now when demonstrating the consistency checking. So we start with this node, and now we go through our concept. So all records stating the rules about concepts, describing concepts and relations, so T boxes. And there we meet, well, we have only one in our case. We have this, so we start with the person. So we look for all records about the person. So what do we have there? And we have that this is a subclass of all persons who have children, right? And so there is a rule on how to expand it, how to expand one node for this universal quantifier. So now I go back a little bit. Well, that's I just copied the formal definition of the rule. So it's best to just to look at this visual example. So what you do, you start to generate. You literally start to expand it. So if it tells that for all, so you start to generate new individuals. So you don't know, so you give some arbitrary names. So you generate an individual child, and then according to the rule, you say, so this guy is a person, and he has a child. So this creation follows from this statement, a factual statement. And to do this, you need to create a new node for the child node, for the child individual. So you don't know the name, but it's somebody. And then actually, I mean, you can. So this rule doesn't end on this. So it means that this child in itself, according to the rule, it may have in turn another child, and you start to generate this node. But of course, I mean, for the universal quantifier, you can generate infinite number of such new nodes. But the algorithm, what it does, so every time it creates a node, it checks if the next one is a subset of the previously created one. So it terminates. So you just say, okay, I mean, for a proof of consistency, it's enough that we generated just yes.
In this case, would it also generate the parents of John? Would it?
That's what happens. No, no. We start with John.
Yeah, but we know that he is a person, so then we should also.
Not an ALC, probably. So we don't have this rule. So we are checking starting from the fact that he is a person. So and according to this rule, he as a person, he has a child.
Yeah.
So if we have another, there should be another relation to another person. We don't have this assertion. So this rule allows to generate descendants.
Okay.
Like children. So this one is a grandchild, and so on and so forth. So it should be a different rule about parents. So a person has parents.
Yeah, but the thing is that it should make general sense. John is a person.
Yeah.
He is like the end of the statement.
This is the statement we have.
Then he should be someone's child.
Absolutely.
Yeah,
Yes. No. No. Because we don't have this statement. And that would correspond. I mean, that would correspond to a different rule. So if we want to generate that part, I mean, parents, grandparents, etc. So then we need another factual rule. But this more complex logics, that's what I'm saying. So this is the difference. You can, I mean, this complications comes exactly from the expressiveness. You can, I guess, in one of the logics, you can say that it's equivalent or some, you put some equivalence to has child and a parent of. And then the tableau would be expanded in both directions. And the idea would be to check all possible branches. I mean, but in ALC logic is whatever we have as a rule, so we check only that. So it's very limited in this case. So if it's not stated about parents, so we don't know anything. But again, just a principle. So what is happening under the hood? So this is an example, and here everything is okay. So I mean, so everything holds according to the rules, so everything is fine. But this is again a made up simple example that we have an assertion. No, sorry, a fact. That person belongs to a class of not persons. It may happen, I mean, by mistake, or I mean, we all humans, so to say, but we can make such a assertion. Maybe it makes sense in some other cases, but definitely, I mean, in case of persons, it's a nonsense. So. And then we start with an assertion. So we see what the algorithm reasoning does in this case. So it actually would terminate immediately. So expanding, when expanding this fact into the first label. So that was first label. So then consulting this axiom, so it will add not person. And what is happening here? So now the logical inference, the logical check happens within I mean this label. I mean what is called label here. So and everything should agree. So essentially it is and logical and this and this. So in this very a simple case, you come to nothing. So this inverse T is nothing, and that means that you come to a contradiction. So you have read error message. So your ontology is not good. So let's see maybe somewhat more interesting example again. So we have a statement uh, about an individual assertion that John is either a human or an animal. So I mean that what again what this assertion you write, and then in the knowledge base, so we have this kind of clear rules that humans are not animals and animals are not humans. So that's kind of um, correctly put inside. So let's see what I mean. Can you guess what will be the result of this verification or of the inference? Should it say yay or nay? Does this statement holds, or should it hold? Yeah, exactly. So I mean, so from the point of view of ontology, so that's a valid assertion. So so your checker should say yes. I mean, at least one branch, well, one branch should come to contradiction. One branch should come to supporting the statement. And all in all, so there is nothing wrong with the statement with respect to the rules presented in the ontology. And again, Tableau algorithm starts with uh, uh, oh, that's not initial. So the initial is without not animal. So so John, human or animal, and then on first step, so you start to create two branches. First, saying that human is not. So if you are human, so then you are not animal, right? So that is the first branch. So you add not animal and human. So that this is the uh, expansion rule for or. Yeah. So I will not scroll back. So it's yes. Um, so basically, you do this expansion. And so if you now look at this node, you do add between all of them. So you come to conclusion that this branch is satisfied. So the second branch would come to a contradiction. So obviously, so the statement that John is an animal while being a human. So that, but all in all, so the verdict will be that the whole ontology is satisfiable. So at least one branch is um, not contradictory. So again, so this is the principle of reasoning behind ontology. So whenever you well, in the part one of lab 3, you will create ontologies and protege, so this pizza stuff, so toppings and such classes. And then you will use reasoners. So behind or under the hood, so the reasoners will start with assertions and roll out a tree based on the factual rules you have, and check each branch of the tree whether, I mean, this assertion makes sense, so supported by the knowledge base. So this is a paper from 2000, May 2000, an overview of Tableau algorithm. So again, so 2000 is the or end of 90s or beginning of 2000 is time of semantic web blossoming. So a huge interest in semantic web. All this RDFS, all stuff is created. People are excited, etc. And so that's what we still have. So let me see. I suggest I don't know, so we are a compact group of people, so I suggest we continue kind of until I finish. If I finish earlier, then will let you go. But I just want to be sure that I cover the second part relevant to the lab. So in part one again, so you will not implement Tableau algorithm yourself. So if you want to know more, so here's the paper. I now want to turn this topic from really pragmatic side, so from this interoperability of technical systems and such, into AI part of it. And I mean, at the end, this course is called Applied AI, Knowledge Representations and Management. So what's about AI? So I mentioned it several times, but again, so I want to ask you, so I mean, why are we talking about AI? In what sense we have been talking about AI versus what is AI and how ontologies are relevant within AI?
What? Can you repeat your question?
Yeah, it's a very complicated question. I understand. Yeah. Probably I should start, just one by one, step by step. What is artificial intelligence?
Something that can handle situations and act upon.
Okay. So what are its main kind of functional components?
Sensors or like
Sensors, good. Sensors.
Yeah. And then how these sensors
how to make sense of sensors, basically.
Yeah. Like what is an accelerometer?
Exactly. Yes. And here we come to reasoning and such.
Yeah.
But now again, so if you noticed, I mean, we talked about quite standard data structures and algorithms for processing these data structures. For us, all this knowledge are just symbols. So a person, accelerometer, or vibration. It's a particular signal. You say it's a signal one. Okay, it's and signal one written in ASCII. So this is a symbolic representation. So, but yes, I mean that is kind of the functionality of intelligence that we want to recreate, and we kind of succeeded so far with this ontologies. But now, so I want to switch gears towards the sensing part itself. So how do you do the sensing in the context of machine learning, or how you do processing of sensing?
The continuous signal.
Yeah, so you have continuous signal. So it's what is continuous signal? It's a physical phenomenon. Yeah. It's electromagnetic field changes in time, or this audio wave, somehow changes. But from the AI perspective, so how do we access this, and how do we treat it?
It's just ones and zeros for.
Yeah, but so okay. So basically, I want to come directly to maybe the processing algorithms for the signal. So how to say that this signal, for example, a vibration from accelerometer installed on a road, that this particular signal corresponds to a passage of a bus, and this particular signal corresponds to passage of a car.
Like different thresholds.
Yeah, well, you need, well, at any in any way you need a block that on the one hand senses something, and then on the other end, so it actually materializes it in some symbolic way. I mean, meaningful. I mean, for a specific task. So traditionally in AI, well, that is say about threshold. So that's more of classical signal processing stuff. I mean, the model-based thing. Well, fair enough. Yeah, maybe. In the area of AI and machine learning, so this task is done by, in many cases, by neural networks, so different kinds. Or at least, I mean, by analogies to how biological intelligent systems do so. So, I mean, the only kind of processing machinery we have are a network of neurons through which we kind of make sense of different phenomena. So neural networks. And historically, so it was like two main camps within, I mean, since the term AI was coined back in 1960s. So there were people saying that AI is all about modeling rules and knowledge and being able to formally reason about it. And those who say AI is about replicating the computational machinery of a brain, of neurons. And as such, and basically the first camp, why what is going on? Okay, now, okay. The first camp about, and what we studied here actually so far, logic, ontologies, expert systems. So that is called good old-fashioned AI, GoFi. So you can find this anywhere. And the second part, so from which all this deep learning stuff and ChatGPT, etc., appeared. So so this camp is called connectionist, a connectionist way to AI. So that's meaning, in a sense that you can process data on the level of connectivity between neural connectivity. Yes. And there are pros and cons. So now we are on the way of converging this. So since quite some time ago, and again, so the reason is to have a unified machinery that can both sense, like process the input as sensor network, so they're really good at it, and at the same time using the strength of structured knowledge representation and formal reasoning. So that's and if you imagine that if you have such a machinery, if this is feasible in principle, then we are kind of on a good way towards kind of understanding how we human actually work. So I mean, they drifted a little bit away towards this discussions about whether we need AI or more capable AI. I think people always forget about. I mean, one of the main ideas with AI is really to understand us ourselves in the first place, rather than kind of create an evil creature. So, but again, down to earth, we have been here And the challenge is whether we can integrate the neural networks and symbolic reasoning somehow. And altogether it's called symbolic neural or symbolic subsymbolic gap. So there is an entire field in AI which is called neurosymbolic artificial intelligence, which roughly speaking combines the neural networks with the symbolic formalism, with knowledge and logic. I will not spell out all these mainstream directions. Rather, I will link one paper, again, a survey paper about neurosymbolic, state of the art in neurosymbolic AI world. Rather, I want to focus on kind of one branch of it, which is, I mean, which is the focus of my research here. So in a way, I am transferring my research interest to this course, and it is something about an area called vector symbol, which is known under different names. So you can find such term as semantic pointer architecture, vector symbolic architecture, or hyperdimensional computing. So this three can be used interchangeably. And the semantic pointer architectures, they come from a group of Chris Eliasmith in Canada. And I mean, he has a mixed background, I think a more soft, like philosophy something, and a technical. So he's a mixture. And one one of his outputs, which is famous, is a book with, I mean, nothing more, nothing less. The title is How to Build a Brain. So if you're interested, so I think it's one of few books which in a coherent manner tries to suggest a theory how to build a brain. So let me just quickly check if I how to build brain. Oops, no, that's too harsh encoding for. Okay, it understood me. Cool. Yes, how to build a brain. So yes, accept cookies. So let's see. Yeah, so it looks like this. You definitely can find some PDF somewhere. But if you have an interest, like a general interest in AI and kind of more broad perspective, so I advise you to read this book. And then now I introduce you I mean, to the main ideas of this theory, which is actually quite easy to understand. But and then I will converge to what I offer you to try in Lab 3. So this particular way of trying to implement a reasoner. So we studied Tableau, but how to implement a reasoner if you have only neural networks. So on the one hand, you have this, say, pizza ontology, very symbolic one. Can you somehow encode it in a neural network? Can a neural network do an inference like this subclass transitivity, for example, inference? So if you think about it, so it's not a trivial business in the first place. And then I hope, hopefully, yeah, I think I will manage. I will walk you through this part of Lab 3 and show you what do I mean with different parts. And I mean, if you have questions, just stop me at any time. So let me see if yeah. So let me give you a very kind of brief introduction into this area of bio-inspired computing or computing, brain-like computing. So I mean, there can be different ways of entering this or explaining this area. You can explain it purely, I mean, based on like mathematical formulations, but I'd rather prefer to kind of introduce it from this hand waving direction where everything seems to appears to be very simplistic. I mean, in terms of programming and operations and on conceptual level. So again, so if you think about it, even without any deep knowledge about neuroscience, you probably know that I mean, um, our brain performs its functions based on activations of many neurons at any given time. So now you sit and listen to me. So every sound I make so activates thousands, if not millions, of neurons simultaneously. A different modality activates a different pattern. So essentially, so all computing seamlessly done by transforming one patterns of activations into other patterns of activation. And then back in, say, end of 70s, beginning of 1970s, beginning of 1980s, so there was this kind of, I mean, some people had this illusions that, well, what if we, how can we abstract away, how can we extract and make this observation useful, computationally useful? So how to perform computations on patterns? So assume that everything is represented as patterns, and not only and moreover, so all these patterns are of very high dimensionality, say thousands. And but now you're kind of computer scientists here, so you tune really towards how to do computations with it. So in our framework, so we won't have ASCII codes. We won't have well, anything else. We only will have patterns. Well, of course, I mean, along the way we can. I mean, for interpretability, we can assign some labels to it. But I mean, from the computational perspective, everything will be just pattern. And one of the guys who actually formulated as a computational framework is Pentti Kanerva, originally from Finland, but immigrated to the US quite a long time ago. He's still active, despite he is more than 90 years old. And so he appears on every webinar I give every second week. So but the idea is okay. So what is patterns? Pattern is not a data structure, so it's something fuzzy. So we actually will we will do some restrictions. So it's not any patterns whatsoever. So these patterns will be of fixed size. And a pattern, so a fixed size, so it means that we will have some number of elements which will have different magnitudes. And again, so we say that so we now will call this this data structures not as patterns but vectors. So vector as a set of coordinates, like in this three-dimensional case, for example. But now instead of three-dimensional, three coordinates, we will have like 10,000 coordinates. And then everything, so you should imagine again, so you kind of place yourself in the world in this many dimensional space, 1,000-dimensional space. And all concepts there are just clouds of these points or vectors originated from some imaginary origin. And there are some mathematical properties I can tell very briefly without showing formulas. Interestingly enough, so first of all, you need to introduce similarity measure. So all computations will make sense, will be performed based on similarity between two vectors. And there is a mathematical way of assessing similarity or measuring similarity. There are well, different ones, but so the typical one is a cosine similarity. So did you see this formula before somewhere? I guess at least in your pre-university studies, I mean, it isn't introduced. So how to measure the cosine between two vectors in n-dimensional space. So it's a dot product divided by the norm of two vectors. But for us, it's important that you can measure somehow similarity. And then, so two concepts. So now think about you somehow encode concepts in terms that we spoke before as vectors. And what we want is that two totally different concepts, they should be dissimilar. So basically, the cosine of it should be 1. So 90 degrees, so orthogonal. Similar concepts, like or same concept is two vectors are exactly the same, so cosine is 0. And then somewhere in between, so you have this gradual similarity between concepts. Speaking of concepts and symbols, so what is symbol if you think about it? So symbol is something that uniquely identifies a thing. It means that, so normally I give this example. So take letters of alphabet so on the one hand, so you have an alphabet where A is or B is after A, C is after B. So there is some kind of order. But from the point of view of symbols, A and B, they're totally, I mean, they can denote whatever things. So they're orthogonal. So symbols are unique entities, so to say. And but now, if we operate in this many-dimensional space, so you want to generate, and if you want to generate symbols, so what you do, you just randomly generate a vector. And there is a math theorems that say that on very high dimensionalities, and that's why we work with high dimensionalities, so two randomly generated vectors will be dissimilar with very high probability, 99%. That means that, I mean, if you ever have a need to invent a tag to something and say this signal is car. So where to get a car? I mean, you remember, so you do all computations just with patterns. You just randomly generate a signal, and you do assignment to it. So that's what I presented. I mean, this pattern is purely from kind of functional perspective. On the other hand, vectors and vector manipulations or vector matrix manipulations. So that's, again, the mathematical apparatus behind neural networks. So you can describe functionality of any neural network through vector matrix operation. So basically, I will not go into this business, but basically whatever I describe as vectors and vector operations can be implemented inside the neural network. So the beauty of this theory that I'm working with, that on the one hand, it has this symbolic interpretation. You can say, okay, this vector is a symbol. It's a concept. This vector is another concept. And actually, I can join them together. So saying that this concept has a tag or this entity. So I can make an assertion basically in the same manner as I. So this entity is this class, for example, and I do it by just an operation which is called binding. I will introduce it shortly. At the same time, so I can do it purely as, or I can interpret this operation as neural interactions. So, and that you will not try in your lab. So you will resort only to vector operations. Hmm? Are we good so far?
I think so.
Huh? No, but I mean, I ask you, I mean, it's not.
Let's say you randomly generate
Yeah.
vectors.
Uh-huh.
So for example, if you have two things that are similar, let's say
Yeah.
a house and an apartment, these things are both buildings.
Absolutely.
Do we want them to stay close or?
It depends.
Okay.
It really depends. But that's a perfect question. In many cases, I mean, in our world, it's not predicate logic. That's a good thing. So, so it's not yes or no. It's not. So there are shades of gray, so to say. So in some cases, you want to regard. So in your example, for example, with the apartments versus house, you want to regard them as some similar entities, like a place to live. On the other hand, in some cases you can really treat them as kind of totally disjoint concepts. So it means that you should have a possibility to do both. So if you wanted some distinct tags to the physical phenomena, and in this case, house and the apartment is a physical phenomenon, so that somehow you sample via your sensors. So, for example, your sensors are uh, a camera, right? So, but sometimes you want to say, okay, that's our totally distinct stuff. So you assign, and in this case, you randomly generate stuff, the tags. But sometimes you want to say that now they are similar. So it's similar from point of view for I can tell you uh, from the point of view of natural language. So when you describe something, so apartment and house, that they bear semantic similarity. And in this case, for example, this word embedding techniques, they will produce you these high-dimensional embeddings, which will be similar to each other. So, or at least embedding of a house and embedding of an apartment will be more similar than embedding of a house and embedding of a cow. So, you see where I'm going.
Yeah.
So there are different ways to generate these vectors, but when the strength is that whenever you want a symbolic, not a tag, you just randomly generate it. And mathematically, it can be shown that they are astronomically many. So you never run out of it. So you don't need to keep a track of consistency of generation. So that's the good thing of it. Yeah, but that's one thing. So you can generate it in different ways. So there is math behind it. So that's good. But I mean, at the end, so they are also vectors, like any other vectors. And as with any other vectors, you can do some operations, algebraic operations. So you can add them together. You can perform sort of multiplication. When I say sort of, so I'm kind of gearing towards more formal algebra. So multiplication sometimes can be implemented by different operations, and that's what we will see very soon. But the thing is that you can do transformations from one vector to another. And apparently, again, the long story short, so this theory of semantic pointers or vector symbolic architectures or hyperdimensional computing, in principle, allows to create arbitrary data structures like graphs. So graph is the most universal data structure in computer science. So all other data structures are just subset of graphs. You can, I will not, well, I guess you will get some insights later on, but you can, for example, you can generate, so maybe I can give you some idea. So take this tree, for example. So you can, you have leaves, you have, well, you have nodes, you have edges, right? And edges go to the left, to the right. So again, one of the ways, like a naive way of kind of encoding this structure into a single vector is to say, okay, I start with the root node. Yes, I start with a root node, and I generate two random vectors for the right and for the left. And then, okay, on the right I have C. So I join these two vectors together by kind of multiplication. On the left, I have, well, I have a nested structure, so which also have left and right. And I also can, well, I can individually describe the branch on the left, on the right, and then join them together by summing up. Why? I mean, so there is a mathematical explanation of why it makes sense, but computationally, so you take all these vectors, some of them you generate randomly. This A, B, and C may be coming from your sensors, but at the end you get a single vector that represents the whole thing, and that's what matters. I mean, that's what you will try in the lab. So you will represent these predicate objects as single vectors. And then you have, so your triple store will essentially be a vector database or vector base. And all inference will be done by operations on vectors. And again, so my hope is that at least you will have some feeling by doing this lab that it actually works and it is interpretable in the case of ontologies. So let me just scroll. I will not go into this stuff. So this is just a description of different atomic operations, what you can do on the vectors. Maybe I want to stop here because I mean there is a keyword binding. Apparently, binding is very. I mean, this term binding is of fundamental importance within AI. And one of the possible limitations of a pure network, neural network approach towards AI. What is meant by binding? I think I mentioned it in some classes. So why it is of fundamental importance? So in our brain, we can wire together concepts into stable patterns. So and these patterns are then used kind of independently of the constituents. So if you have red, so a concept of a red, so that's a atomic concept of your feeling of red color, and a concept of a house. So you want to say so when you see a red house, so you have a separate notion of a red house on the one hand. So you can just use it in other constructs without decomposing it down to original concept. So you can just say, okay, describing the road, you say red house on the left along your way. So you assign a symbol to a red house, and this assignment of a symbol is called a binding. And the inverse part of binding is unbinding or factorization. So looking at something, at an object, like a table or any other object, you can decompose it, you can unbind the stuff mentally and describe each part individually. So that's connected to what we discussed about partonymy yesterday. That appears to be the strength, the most fundamental functionality of human intelligence. And apparently, it is not obvious how neural networks do that. So if you think about it, so I guess, well, I don't know, did you have any class on machine learning or something? Huh?
Yeah.
Like neural machines or something?
Yeah.
Or what?
You just went through different kind of neural networks.
It was introductory,
Yeah.
maybe. Yeah. But the thing is that so neural networks is just you have this complicated learning procedure. So if you can think about training a neural network on images like horses, dogs, and stuff like that. So yes, they can classify, but they have no notion that that horse has like 2 legs or something. So it's only post factum you can kind of analyze and see that okay, some neurons may be tuned more to features which look like legs, while some others which look are tuned more to something which look like face. And the same thing for ChatGPT and such. I mean, yes, you can. I think sorry if I repeat myself, but you can ask, so what a table consists of, and it will explain you. But where this information is actually stored, because ChatGPT is like a huge neural network, that's unclear. Yeah. So, and that's why. So that was a long story about importance of a challenge to implement binding in artificial intelligence. In our framework, binding is done very naturally by just kind of multiplication. Again, you will understand why I say kind of multiplication. And in vector space, in vector algebra, it makes sense. You multiply 2 vectors, you get a vector. Then if you can easily, if you know one component that you bind with, so you take this new vector, you can unbind it, you can extract it, and you get the second component. So it makes sense, like intuitively. And so there are different kinds of operations you can do. So you can implement multiplication, which is more associative. So you can and distributive with respect to operands. So you can change the places and such. In ontologies, and I have a slide on this, it actually matters the order in which you bind. So if you bind the predicate to an object, it's not the same as you bind object to a predicate. So they just come into a wrong place. And you will see this special kind of multiplication, which is called vector. Oh, I always forget this vector something binding, vector transformation binding. Yes. So let me go directly to the lab. So I hope I gave you some ideas that, I mean, how this brain inspiration about activation of patterns, formalization into vector operation makes sense, and that vectors, vector or matrix vector operations, they have direct kind of incarnation in neural networks. So that's kind of end of story. So let's, if you want to know more, So you will find some resources. So I myself lead webinars like since 5 years ago. Plenty of videos and a dedicated website if you want to know more. So now to the article. So the key component that you probably should understand, I want to explain verbally, is something which is called vector-derived transformation binding, VTB. That's the key term in the paper. At the end, we are implementing binding, as I said. So, and again, what we do, we live in this vector space. So we have concepts encoded as vectors, and we want to join them together at some point. So for example, again, so we will encode triples, subject, predicate, objects. And we will encode it in a way that we want to so for any given subject, we want to make association to all the predicate object pairs somehow in a vector form. So we want to join the or bind the predicate and the object, and both of them in the at the end are vectors. But the binding would we need. I mean, the way how it is presented in the paper will turn one vector, which is actually the vector for predicate, into a matrix of special form. So basically, you have a vector y, so or p, your predicate. You generate it randomly, but then you form a matrix. And how you form a matrix? You fold this vector into a small square matrix. So, and that means that the size of your vector should be chosen such that you can form a square matrix. So, for example, if you choose size of your vector 4, then you can fold it like say stack to so split it in half, make first half first column, second half second column. So you get a matrix 2 by 2. If you have 9-dimensional vector, so you can fold it into matrix 3 by 3. So that's your basic building block B prime. And this, and then what's interesting, so the, it's not, I don't know if it's interesting or not, but what you can do, you can form a bigger matrix out of these blocks in this way by placing them on the diagonal. So at the end, you will compute a matrix of the dimensionality d by d. Is this kind of clear? So you start with the vector of dimensionality d. From this, you make a smaller one, a square matrix, and then you place them on diagonal. So if you have dimensionality 4, so it will be 2 matrices 2 by 2. So these matrices are all same. They just appear in the different places of this bigger matrix. And this is a code to generate it. And then that's what I say. So you want take this matrix, and you want to bind with the vector denoting a certain concept. And you do it by matrix vector multiplication. So if you want to unbind it, so you do an inverse of this matrix, and apply it to vector z, the one that you produced before. So Now, maybe now it's a good time to stop this presentation and rather show you the lab itself. So the presentation is available in PDF, so you can read it. So and you have a paper as well. So let me see, file, open folder, which one I want? I think it's this one. No, that's solution. Open, save on. Lab 3, yeah, this one. So what you are given a stub code, a Jupyter notebook, where which uses in turn a library, so the methods for this matrix vector multiplication and manipulation in SRC folder. So I want you to, again, read the paper and implement the major steps. So what I explained you so far is the concept of binding, and this will be used to encode predicate and objects. I also mentioned that the subject will be accounted as as association. So I mean, you should think of it as, so instead of kind of keeping triples, so subject, predicate, object, and repeating subject and subject and subject. So you have a single entry for subject, which is an index to all predicate object pairs. And by doing this, like in normal kind of classical programming way, so this indexing, this thing is called associative memory. So by knowing the key, you retrieve associations. So that's the meaning of associative memories. So, and you will have several of them, or you will have two. One for assertions, and another one for or facts, and another one for which encode entailment rules. So, associative memory one will be for facts, and associative memory 2 will be for entailment rules. Yeah. And here you will be given some numerical examples of small dimensional vectors. So those are given to you to actually verify your computations. But in reality, I mean, all these vectors or concepts should be encoded by just randomly generating high dimensional patterns. Yes. So you're not protesting. So like everything is damn clear.
See when we look at it next week.
Okay. Yeah, fair enough. Fair enough. But we will be here for you. I mean, so yeah. So let me just walk you maybe. So in the remaining time, let me walk you through this example. So I don't know why is it. Let me see if I can use this one. Yeah. Okay. So that's. By the way, did you did you open the zip? It just came to me that I mean it might be that you don't see the images. Can you check? But okay, nevertheless. So let me see. Where what was I? This is the scenario. This is the scenario. So you're given this small part of the ontology. So Luigi is a person, and he eats this pizza, and pizza of type margherita, and which is subclass of pizza, which is subclass of food. And so this black arrows is your facts that you put in your knowledge base. What you need to infer is the subclass, the transitivity entailment. So that this pizza is also of type pizza and also of type food. And margherita is a subclass of food. For this, you will need to encode these individuals as vectors, and I have already said. So in this case, everything, so all the instances that you have, they should be randomly generated. So I suggest again. So maybe I mean, if you didn't read the file before, it won't be very informative if I try to explain. Rather, so we tried to actually navigate you through the process of programming of this stuff, and so you just need to fill it in with appropriate calls for functions in the library. Or, for example, generate vectors randomly. Right. So maybe again, if you don't have specific questions, I would stop at this point and wait for your reaction next week. So we try, Mons and I will try to resolve these questions on the fly. And as I said, I give you 2 weeks to complete the whole lab. So I want to try it on you. So let's see. So as I said, maybe no, I won't say anything about you see the point settings. So meaning that total failure wouldn't totally fail you, so to say. But I wanted to try this and check how I can do next year. No, the home assignment will be published in 1 week from now. So basically, you will have 2 classes, as I said by my guest lecturer. So he will be streaming from Melbourne. After that, after the second class, or maybe after the first class, we will publish the assignment. It is related to what he is presenting. And it will be practical home assignment. So basically, you need to experiment. I cannot see the image in Python notebook. Okay, good that I noticed. So I will update now or today. Okay, good. So good luck with quiz and everything. So I think now by the end of the course you have quite some intellectual things to complete.